Like when I showed up, someone already told me.
Now they're all gonna go and
they never see me and then check it months, like I got busy with the actual term, checked it a few months later, and they gave up.
All right, let's get started. We've been recording now for like 10 seconds, so the beginning of the lecture is just gonna be the whole classroom talking.
Okay,
Great.
that's good.
Yeah. I don't know how much it picks up from you guys talking. Maybe the microphone's not that powerful. But we're on lecture 19, order finding. So now we're getting to the end of the different tools that we need to do Shor's algorithm in a quantum computer. And so this is going to be the last ingredient. I still don't know if I want to, we'll have all the ingredients. I still don't know if I want to go through it explicitly, but maybe just roughly in the next lecture. But hopefully this is going to be it. And there's going to be one result that I think I might just skip because it's just computational. But anyway, so this is where we stand right now. We have n, which we want to factor, and we find x, which has GCD equal to 1. And then we define a unitary operator, which just multiplies numbers by x. And we've determined that we have an eigenvector, u sub s, that has eigenvalue 2 pi I s over r, meaning that the phase is equal to s over r. And the explicit expression for u sub s is given here. And the goal here is to compute r. So once we have r, and if r is even, we're going to have that the GCD of this quantity or the GCD of this quantity is going to be a non-trivial factor of n. So at this point, we're getting close. We have that the eigenvalue of this operator is related to r. But we still need to extract r. That's the last thing that we need. Because once we have r, then we can just find the factor. And the idea here is to use the phase estimation quantum circuit, which, bless you, we've seen in the previous 2 lectures, and it's given by this diagram. You start with the zeros, and then the eigenvector. And here, this is going to be t qubits initiated at 0. And t, the number of qubits, depends on the precision that you want to measure the phase of the eigenvalue us. And if you run this quantum circuit, then the output is going to be us, and then an approximation of the phase, which is going to be an approximation of s over r. And in particular, this output is going to be a linear combination of numbers where the magnitude or the amplitude of these numbers are going to be concentrated around s over r. So, and here, in other words, I say that the magnitude, the probability of having numbers in this linear combination is going to be small if m over 2 to the t is far from s over r. So, and you can make it, or not far, even like just a little bit away, then you can make it that if it deviates by more than 2 to the minus n, then the probability of measuring that is small. And here we determined that to have the precision, this precision, 2 to the minus n, and with this probability, then the number of qubits that we need is n plus this quantity. So again, since we have this operator ux, the goal is to get r, and we have that r is in the face of this operator, and then in here, the phase estimator is going to give us an approximation of S over R. It's going to get us close to R. But there's at least 2 issues going on here. Question, yes?
Phase is missing an H. Yeah.
Pace?
I mean, it's a passe estimate.
Passe.
I think that might have an extra S in it, but yeah.
Passe. Is that actually a word in some language? Passe?
I think it's French. I think there are 2 S's.
It's just, I mean, you could say dépassé.
Dépassé. I passed you.
So true, so true.
It's just. Now, just for fun, I made a planet H. All right. Other questions?
I'm fine.
All right. I'm pretty sure I've had typos all throughout class, so I wonder why today we decided to actually point out the typo. No, it's fine. It's I've never claimed to be a great speller. There's this. So I've been talking to other colleagues about ChatGPT and how we need to start addressing it in class and say when it's legit to use it or not legit to use it. But I started thinking about writing my papers with ChatGPT. Not necessarily do the math, but just write the introduction or stuff like that. I still, the only problem is that I still don't think that ChatGPT captures my voice. I have a unique way of writing that I think is unique to me, or I think I have a unique way of writing. But ChatGPT at this point is not capturing that, so I'm still not going for it. But anyway, ChatGPT would know there's an H there. So that's confirmation that these notes were not written by ChatGPT.
It's how your voice is. It's not.
Yeah, my voice would say passé. So anyway, so we're trying to get R, and we've seen using the operator UX, we see that R is in the phase, and so the idea is to use the phase estimation circuit to approximate the phase. There's at least 2 issues with this idea. Can anyone think of what these issues are? Since there's 2 issues and we have 2 sides of the room, one side stage left is going to come up with one, and stage right is going to come up with another. Stage left, what do you have?
Which side is that?
That side.
That's house left. This is stage left.
Well, I think we're in stage.
Stage right.
That's stage.
I'm
This is
Oh, you're stage.
I have the stage.
I see.
Stage right. We'll
That
split it
makes
up
more
here.
sense.
Stage left, we'll split it up here.
I'm going to switch chairs for a minute.
Here, I'll give you a hint. There's one issues with this and the other issues with this.
It might be non-trivial to construct the initial state.
Yeah, so this. And so let's look at the equation for u sub s. So for u sub s, what ingredients are we're looking at here? what ingredients do you need to construct this vector?
You need R, SR, and like you still don't know. You don't know the difference between SR and R.
Well, you're getting close to it. So the whole goal here is to compute R. So at this point, we actually don't know what R is. But if you look at the formula of u sub s, what do you see there? R. So we can't really construct u sub s because we don't know what R is. So that kind of like chicken and the egg type of problem. So we're gonna resolve that. That's actually the biggest issue, that we don't know that. And then the second issue here comes from here. What's the problem here? We need to know R exactly. And this v tilde is only an approximation. So when we measure it, we might not get S over R exactly. We might measure something else that's going to be close to S over R. And in most cases, S over R is not going to have a terminating base 2 expansion. So that means that we can never get it precisely 100% accurate. We can only approximate it. And in the second issue, we need to figure out a way to actually obtain R exactly from the approximation. So those are the two biggest issues. So obtaining R is going to be a technical issue that we can get around it. And u sub s, since it depends on R, it's a little bit more tricky. So we have to find another way to get around it. And here is the idea. This observation, this identity, is that if we take the average of a uniform average of the vectors u sub s, then we obtain this this vector 1. And in here, the right-hand side is independent of R, but it's made up of things that depend on R. So what we're going to do is we're going to instead work with 1 instead of each one of these. And from the 1, we're going to be able to extract R. So the first thing that I'm asking you to do is to verify this identity. So I recall the definition for u sub s and use this other identity. So I'll give you a moment to work on that. What do you see?
So I was gonna take the and then try to work from that.
Oh, from the hint? Or from what?
I was gonna try working backwards from our result. So I was taking that and I was gonna put our not really definition, but we know use of S to be put it into that.
Yeah, so start from the left-hand side and then substitute use of this.
Yeah.
Yeah, so yeah, that's the way that you should do it.
Okay.
And then at some point you're gonna come up with this the hint.
Okay.
Questions?
Yeah, so I was just thinking.
You see the sun there for heating for Mars. So that
Not yet.
our one times X
Just substitution.
and I think everything else makes sense.
And then you apply to him.
Maybe a little. Not too bad. Okay.
You should write bigger.
Should I do this?
I'm kidding.
Oh yeah, you wouldn't have to get some. Yeah, I got my dark pen.
Why not?
For the reason.
Because the quantum of
Oh, close.
so it changed the summation.
So,
Or,
Double check me, I remember that.
well,
yeah, but actually you need the geometric sum. I think you have to use the hint at some point. And like, from what I remember, you already flipped the so I think you can just use the
Does the hint come from geometric sum?
I forgot. I think so, but yeah, I think so. I don't remember, but
A little, I mean, well, oh, I guess so. That's about as it comes out. Somehow that won't be equal to one.
it's all zeros except for.
well, it would be equal to 1, and then you're summing 0 1 arrow times. So this is either going equal to 1 or 0.
It's much faster.
Yes.
I'll just instead of doing
But yeah, so yeah, I think you're deriving the
I
hint.
can just start from. If I just do
I'm just stuck with that.
That's the one.
Oh,
And also, for application.
What do you mean you already had it?
It's all the exercises.
Alright, sorry, let's see.
Substitutions.
is the problem concerning is the real number switched to some.
Yeah, finite sums. You can always skip.
But,
That's a good thing. We want these.
yeah, you substitute, you take out the keys, because you went somewhere else. I was just sure you could do that or not.
Looks like you got it.
So you used to just hands down.
Yeah, finite sums you can always. Yeah, so the only k that will survive is 0, so it's k x to the 0. 1. Okay. So yeah, for this problem, it's just substitution. You substitute the formula for u sub s, And when you switch the summations, which for finite sums, it's always doable. R minus 1, and then E minus 2 pi I k s over R. I think I have it right. And then xk, so this is in here, mod n, and then you have 1 over R, k 0 to R minus 1, R indicator function, k is equal to 0, xk mod n. So at the end, you just have 1 mod n. Does that make sense? All right. Now I'm gonna do an example. Because in here, we're gonna use the same phase estimation quantum circuit, but instead of using the eigenvalue u sub s here, we're gonna use the vector 1. And we gotta see, so when we use the eigenvalue, then we saw that it estimated the phase. Bless you, bless you. But when we use 1, we wanna see what it estimates. So instead of putting us in the bottom bits, then we're gonna put 1. And we know that 1 is a weighted average of the eigenvectors. So we start, and in here I just have 1 qubit. And in here, this is just for demonstration to see kind of what to do. 1 qubit, which started at 0. So we're gonna start with 0, 1, and then we apply the Hadamard gate. So the state here is gonna be psi 0, which I'm just applying the Hadamard gate to the first qubit, and it's just gonna be 0 plus 1, and then I expand it, and it's gonna be 0, 1, and plus 1, 1. So we're familiar with this computation, and this is where we are. And then we apply this controlled U gate. And in here, that means that psi 1 is gonna be, due to a control, it's not gonna act on this qubit. And based on the control, U will act on this qubit, on this vector. So far so good. Is this make sense? Psi 1 is going to be this vector. And what I want to do is I want to figure out this action of u sub x and actually like write it in a clever way that's going to be good for computations. So again, for the second vector, we have that 1 is this linear combination of the eigenvectors. So we have that if we apply u sub x to 1, then we can do this linear combination for 1, and then we use linearity to bring the operator ux inside. And for each of the eigenvectors, we know that the action is just a multiplication by the eigenvalue. So we have this. Alternatively, by definition, we have the u sub x of 1 is equal to x, but we actually want to write it this way. We want it in the basis, in the eigenvectors. So going back now to psi 1, we have that this is psi 1, and then we apply u of x on this vector, and based on this computation, then this is going to be the result. Which at this point, that's messy looking still. It's not something that's friendly, but I kind of want to put it into a format that's going to be better for computations. So I observe that this 1, I can do this substitution for this 1. So I can write that 1 with that sum, so I can write this sum this way. So this is equal to this. And now I'm summing over the eigenvectors from 0 to r minus 1. And in this case, I have the eigenvalues. So I can write psi 1 to be this linear combination, where we have this as the first qubit, this linear combination of 0 and 1, and then we have the eigenvalue there. Does this make sense? And the whole reason why I want to write it this way is because we want to apply, after we apply the control U gates, for the phase estimation quantum circuit, we want to apply the Fourier inverse. And for the Fourier inverse, it helps to be in this format. So that's what we're going to do next. So in this case, assume r is equal to 2, the phase is equal to 2, and we have 2 qubits. And we apply the phase estimation circuit. And we obtain some psi. And in fact, psi is going to be able to be written in this form, where you have the eigenvalues of us, and then you have s's, which the s is going to go from 0 to r minus 1, and then some amplitudes, alpha 1. And the question here in this exercise is compute alpha 1. So now take a moment to figure out what the alpha 1s are. And here I've already, in the previous computation, I already did the computation for this part, essentially. And doing the similar ideas, using the similar idea or computations, you can compute this part too. So based on the previous computation, you should be able to get here. And then you apply the Fourier inverse. So go for it. And if you need me to go back in the computations, I can do it. Maybe I'll add some notes. 1 is equal to 1 over square root of r. So first, try to compute what's happening up to this point, we know what's happening, right? Each of these zeros becomes 0, 1 and 0, 1. And then try to figure out what happens here. And that's the computation I did in the example before. Nothing's happening to this. And then here, it's just the computation that I did, this too. Try to figure out what that is, and then the next step is try to figure out what's happening at this point. And then apply the Fourier numbers. So try to get to this point. And once you're there, it's either going to make sense or it's not. And then I can take it from there. How's it going? Where are you?
I was just trying to do what happens in the first case.
So maybe I'll flip back.
Yeah.
So this is just going back to the first case, what happens. And this was for this circuit. H, U, this is 0, this is 1, and then this, psi 1. So in this case, the result was this. And you should think about what happens when instead you do
This is also for here,
so for this circuit, the first computation is going to be computing this, which corresponds to this circuit here, which we already did. The second computation is computing this, which corresponds to this circuit, which is essentially the same as this circuit, except it has a square. So you have to figure out how the computation changed in that case. And then you're at this point. And you should be able to get at this point based on the previous computation. And then either you're going to recognize what is happening at F inverse, or you may not. And that's where I'll come in. But I'm hoping that you'll be able to recognize what to do at the F inverse. But at this point, try to focus on this second diagram and see if you can do it. And get to the point right before the Fourier inverse. Is that UX squared or cubed?
That's 3.
Where's the 3 coming from?
Because the linear applied at 3 times, right?
but have two different qubits. I see what you mean. But the first one just transfers to and the first one usually is gonna have like so at this point we have that this is going to be u. This is going to be this. What do we say? It's going to be 0 plus e to the 2 pi I s over r 1. And then s from 0 to r minus 1. And then, so that's for this one, 0. And then we have, this one is going to be 0 plus 1. And then u. So when you apply it, when you go to this point, you're going to apply it in this one. So you're applying u squared. Here. And then the s over r's are going to go into this thing. So when you apply it the first time, the s over r's are going to go into the first qubit. And then you're going to apply again u squared. And then you're going to do the manipulation so that they come in here. Does that make sense? Did you get past the two control U gates?
Yeah, it went the same way with the game languages. It should be the same
Yeah.
thing, it's just different.
The tricky part of this and then a lot of this computations is that it helps to put in the right representation to actually see the answer. So in here, that's why I'm pulling the S or R's for the first U here, and then in the second one here. And then it's going to put it into a format for your inverse. Makes sense.
There's too much to write from the right device. Here's just
Looks like you're in the right track. You might run out of battery.
yes. I have my charger, so I'm trying to grab this.
Alright, so this is not a book.
It does not look like it.
So how's it going?
We'll just have to use it, just try not to use it, but it doesn't look very good.
That's the whole thing.
And
Yes. Yeah,
just in writing the second gate.
So for the second drawing,
Yeah. So I know we'll be applying
u squared,
square, so what did,
it's just times 2.
just use,
Because it's lambda times lambda squared, and lambda squared is the height. It's times 2, exponent.
yeah, so that would be
4. Yeah. Yeah, and that would be it for the second one. And then you kind of just have to put it together here. How's it going?
Just
because, yeah, you have,
On the first line, we're going to sign one, like,
yeah, that's the two possibilities where, it's only the one that has the lower one with the, control line, like actually, that's the use.
So let me just psi1 prime, let's call this psi1 prime. Then this is gonna follow the same type of computation, and it's gonna be 1 over square root of r s equals 0 to r minus 1, and you have 0 plus e to the 4 pi I s over r 1 u s. And it's because we're applying u squared, so it's gonna be the eigenvalue square. So in here, this essentially takes us, I didn't write it, add a page. So this takes us to this point, and that means that that is going to be, so that actually, let me just, we don't need this. So at this point, the result is going to be S1, S2 from 0 to r minus 1, and the first one is 0 plus e to the 2 pi I s over r, S1, times 0 plus e to the 2 pi I, 4 pi I S2 over r, 1, and us. So at this point, this is the state. So it's from the first one, we do the first computation. From the second one, we do the second computation, and we put them together. And this is what we have at that point. And then this is now when we apply the Fourier transform, and we apply it to this two qubits. And this is how the Fourier transform is defined. And the fact that r is equal to 4, that means that this s over r has a terminating base 2 sequence. It terminates in two things. So we are actually going to get the exact values for the Fourier inverse. So in here, this is actually going to be, the Fourier inverse is going to map to it's going to map to 1 over square root of r s from 0 to r minus 1 of s, and actually I think I made a typo. I think this is just s. They're just both s. It's one summation. And then this is going to be s and u sub s. So the answer for this find the coefficients is that alpha, and there's supposed to be alpha sub s. Alpha sub s is equal to 1 over square root of r for all of them. So the thing for this computation is that you gotta recognize that you can write this in a nice representation that has a nice Fourier inverse. And this is the representation of the Fourier inverse that we've been using. Let's see if I can get to it. Fourier inverse. Yeah, so here's the representation of the Fourier inverse, where it maps M to this type of products, and that's what we have. So that's why we can map it back. And so in this case, that's what we're going to have. And And here we'll explain what's going to happen when it's not terminating. But that's it for now. That's class. Have a good weekend.
So those Lorentzians,
Lorentzians?
like the distributions,
Oh, no, they're just drawings. They're bumps.
it's like that's like the fourth Lorentzian.
No, it's just like where the probability is concentrating around which numbers.